So I'm Kirk Borne. I'm currently the principal data scientist at Booz Allen Hamilton. I live in this area. Booz Allen Hamilton is a global consulting and technology company whose corporate headquarters is right across the highway here. I actually work in Central Maryland, and I've been with the company for 4 years. Pretty much in my roles, I do a lot of mentoring and training, executive advising, a lot of public speaking and writing and things like that, and also very active on social media. Anyone follow me on Twitter? Thank you very much. I appreciate that. I'll pass out dollars at the end. So I don't have swag like the other people do. So thank you for coming today. So just a little bit of background so you see where I'm coming from with this. So 4 years at Booz Allen, and the 12 prior years before that, I was a professor of astrophysics at George Mason University, which is right down the road from here. So I didn't teach astrophysics. I taught data science. So we actually formed the world's first undergraduate data science degree program at George Mason, which started a dozen years ago. And so I did that. I did teaching there at the graduate and undergraduate level for 12 years. Astrophysics, because my background is astrophysics. I spent 20 years before that running NASA astronomy data systems, so data systems for NASA astronomy satellites, including the Hubble Space Telescope. So I tell people my day job was data and my night job was data as an astronomer. So always working with data and always looking for patterns in data and doing discovery with data. And so we get to play in that space and in very much abundance nowadays. We're all living with data, trying to find patterns, meaningful patterns, beneficial patterns in our data that we can derive value from and go forward with that. And so sometimes it's hard to know what patterns make sense. So when I started doing this machine learning data science, which we call data mining thing about 21 years ago, not so much called data science, it was really just data mining, but it was the same machine learning algorithms we use today, basically. So when I was doing this with astronomy data at NASA, my astronomy friends said, what are you doing? I said, I'm doing data mining. And they said, well, what's that? And I said, well, we're looking for patterns in data. And they said, oh, that's just a fishing expedition. If you look hard enough, you'll find something, right? If you throw your line in the lake, you'll get something. So what does it even mean? So the trick is trying to decipher and interpret the meaning of the patterns you find in your data. And so that's what this talk is about today. It's about the cold start problem, which is what do you do with data in a way that makes it actually more than just a fishing expedition. You actually find the meaningful pattern, sort of the optimal pattern, if you will. And so it's not so much about supervised learning, though I'll mention how this relates to supervised learning as I go. But it's really more about the unsupervised learning, that when you really don't have sort of something to guide you. For example, in supervised learning, you have labeled data and you have training data. Okay, so you have something to guide you. You have examples of things that are labeled, like images of cancers in lungs or images of defective heart valves. You have images, you have examples of things that have already been labeled and classified, and you try to build a model that learns what are the features of that thing so you can classify new examples. So we understand supervised learning, you're given something to begin with, okay? So it's not a cold start problem. You already have fuel in the tank, you have the engine running, you already have the map, you already know where you're going. So with cold starts, you really don't know quite where you're going. So the whole point of this is it feeds into this fundamental reason we exist in the world, data scientists, most in-demand profession in the world, as you know. So part of the reason is because our job and our role is quite significant, which is to discover the value that exists in these data collections, that exists, and the patterns that we find in these data collections. And so we do that through a methodology called data science. Okay, so it's a scientific methodology, and we do that throughout mathematical algorithms, which we call machine learning. So I had this definition of machine learning there, which you will see materialize in one way or another throughout this talk, so I emphasize it now. When I first started reading about machine learning in 1997, okay, so 22 years ago, I ran across the textbook of the day on machine learning by Tom Mitchell, and he defined machine learning as algorithms that learn from experience, period. Algorithms that learn from experience. That was the definition. When I first saw that, I said, what the hell does that mean? Okay, it was a little too simple. But as the years go by, I realize now it's extremely profound in its simplicity, because it's really about how do you get feedback to improve the algorithm, improve the classification, improve the pattern detection, include improve and optimize the results of our experiments, our machine learning and data science experiments. And so algorithms that learn from experience, it's that feedback loop. So just a very simple example, which you'll see later also, back propagation in neural networks. That back propagation step where you estimate the error in your network, in its classifications, and you figure out what changes in the weights of the network, the edge weights between the nodes in the network, how much change to apply to each one of those weights in order to improve the accuracy of the algorithm, right? And so you're back propagating the error. The algorithm, the network is learning from experience. The experience is the data. Okay, so humans are very good at doing this. Okay, so one thing I like about machine learning is it's easy to explain to school kids and to grandmothers and to data scientists all in the same description, because it's all about what humans do naturally. Okay, humans naturally detect patterns and recognize patterns. Okay, so when the first cave people came out of the cave and they would see an animal in front of them, they were detecting a pattern. All right, they had to recognize what the pattern meant, though. Okay, is this animal going to eat me for lunch, or is this my lunch? If you make the wrong decision, either way, it's the end of your life, okay? Okay, so you have to be able to do a good pattern recognition, that is classification, recognizing what it is, not just detecting that there is a pattern. Okay, so that's the key there, is it's not just the discovery of it, but it's recognizing what it is, because that empowers decision making. It empowers you to do something once you recognize what that pattern is telling you. So if you're doing like, for example, lung cancer screening, and you see a blob in a lung, in an image of a lung, is that blob an infection? Is it a bruise? Or is it a cancer? I mean, so they may look similar to the untrained eye. They don't look similar to a trained eye, but that trained eye, that oncologist is an extremely expensive, busy person who maybe can only look at these lung scans once every couple of weeks or something, and so you may go in for a lung scan for a cancer test, and you may not get a result for 2 weeks. Whereas if you have a machine learning algorithm running in the MRI tube, you can find out immediately. Maybe they won't tell you immediately, but at least they'll tell you something like, gee, the scan didn't turn out too well. You need to turn your body the other way. Well, nice to find that out when you're still in the tube instead of 2 weeks later when you finally get the call from the doctor and said, oh, by the way, we can't tell you the results of your test because you need to do it again. Okay, so being able to recognize patterns enables decision making. But at the end of the day, it's not just decisions. We really want to explore these patterns for the value they bring. Again, so our job as data scientists is to find that value, innovating from these patterns. We explore them to do that. And then ultimately, we go from exploration to exploitation, where we actually generate that value and generate those actions from all our data. So that's really the easy button for what we're talking about. Okay, so there's lots of math behind those statements, but this is really basically what we're doing. Okay, here's another way of describing what we're doing, again, without the math, but with pictures this time. Okay, and so when we're talking about pattern discovery, pattern detection, and recognition, I like to put it in these 4 categories. So this is a very broad brush way of describing unsupervised learning. Okay, it's either a class discovery, that is segment discovery, or clustering, if you will, but basically finding the segments, clusters in your data, as shown in that diagram in the upper left. Okay, that diagram on the upper left has data clouds 1, 2, and 3 in it, and a parameter space, P1, P2, P3. This is fake data, toy data, make-believe data. In astronomy, it's called the banana diagram because data cloud 2 is shaped like a banana. Okay, personally, I like to just call it the peanut, banana, and potato diagram. But what you have here is, as you add more data points, you start discovering the classes, the segments, the clusters in the data, and there may be more such clusters and segments in the data as you add more data points. And as you add more data points, you start now understanding what are the segments in the population, but what distinguishes them? What are the boundaries between them? How much separation is there between them? For example, data cloud 2 and data cloud 1 have clean separation, but data cloud 2 and data cloud 3 are not very cleanly separated, okay? So if these things become, for example, cancer diagnoses in some parameter space of medical test results, if your medical test result lies near the boundary of DC2 and DC3, whatever those are, you know that there's a high likelihood, or a likelihood, a reasonable likelihood of a false positive or a false negative there, because the boundary between those two classifications is fuzzy, some overlap there, so very close. So you're learning things data-wise as well as domain-wise when you do things like this. So class discovery is one thing. The next thing we discover here is trend discovery, correlation discovery. Okay, X versus Y, right? We find that Y correlates with X. In a sense, that's a form of data reduction, dimension reduction, because if X implies Y, then why do you need Y anymore? You just need X. It'll tell you about Y. Okay, so X implies Y is correlation discovery. And most typical correlation discovery we use in predictive analytics, okay? So it's predictive power discovery. That is, given an X, you can predict what a Y will be. But I like to say it goes beyond that once you have more than 2 dimensions. Once you go beyond 2 dimensions, it's not just Y is a function of X, but Y is a function of X1 and X2, or in this case, P3 is a function of P1 and P2. All right, so what I would like to say, what's been interesting about that, as we have, for example, in Data Cloud 2, we have this trend, okay, between P3 and P1 that's sort of shallow initially, all right? It's sort of shallow, and then the trend, the slope gets steeper on different values of P1. In this case, lower values of P1 produce higher values of P3. So we learned about this correlation, but we don't quite understand what caused it. How can you understand that? But so we have this other dimension now. P2 is telling us something about it. That P2 is some kind of additional contextual information about the point where that transition changes. Now, if P2 happens to be something you have control over, so in statistics, it's called a treatment variable. If that's a treatment, if P2 happens to be something you can control, for example, let's say the P3 is basically sort of the predicted failure rate for a particular machine as a function of the age of the machine or something like this. Well, you can't really change the age of this machine. It is what it is, right? So P1 is not in your control. But P2 might be something like operating temperature or revolutions. I mean, the speed at which you run the engine. Okay, so the higher the temperature or the higher the speed you run the engine, the more likely it is to fail. That's something you have control over. And you can see where that critical point is, so you can operate below that critical point. Okay, so having additional dimensions, some of which are, again, contextual that you have control over, not all, but if you do have some of those, look for them in your data. I would say look for them in your data, because after all, we all have lots of dimensions on our data. Find the ones where you see these dependencies in something you have control over. That now gives you what I call prescriptive power discovery. It's prescriptive analytics. You can now change the outcome. You can now achieve a different outcome than what, Y, find Y given X. I say, given Y, find X. Okay, so initially it's given X, find Y. That's traditional prediction. Given X, find Y. Prescription is given Y, find X. I don't like the outcome you're predicting. I want a different outcome. What are the conditions I can set? So find the values that I can set to achieve a better value for Y. Okay, that's prescriptive power discovery. Okay, so the third one, I'll move a little faster now, is the anomaly detection or outlier detection. I think that's such a negative. I like to call it surprise discovery. So when I was at George Mason, most of my graduate students learned this from me, that most of their dissertations were on the topic of surprise discovery in data, because that's finding the interesting, unexpected, surprising thing in your data. Okay, so it may not be an outlier, it may be an inlier. Okay, so an outlier might be something that's 3 or more standard deviations from the mean. Okay, but if you have a pulse rate like this in your heart and suddenly it's like this, okay, it's right near the mean, you must be okay. It's right at the mean, you must still be alive. Wrong. Okay, so imagine a machine like that. So you set alarms on your machines that when some signal goes 3 or more standard deviations from the mean, you get an alert. Well, wait a minute, what if it's right at the mean when it shouldn't be? That's an inlier, and an inlier is a surprising, unexpected thing that you do also need to be alerted on. Okay, so these are patterns we can find in our data, and again, these are all unsupervised. There's nothing about these things where I'm actually putting a label on them or putting a domain specification of what this means. I'm just giving you examples of what it might mean, but these are all unsupervised pattern discoveries. And then the last one deserves its own little chart at the bottom there, which is link discovery. Okay, finding interesting connections in a network, okay, whether it's a knowledge graph or it's the internet. Okay, so a small company by the name of Google basically generated its trillion-dollar industry or valuation just from an algorithm called PageRank, which is finding authoritative nodes in a network. Okay, and it's unsupervised. Okay, no one came along and said, hey, here's the most important node about NASA astronomy data. I hope it was mine. Here was the most important node about NASA data mining for space science. That was mine, by the way. It was the #1 thing. Okay, but no one told them that. The algorithm discovered it. Okay, and it found it by doing network science and applying algorithms, metrics, to find authoritative nodes and networks, as well as degrees of separation and inbound and outbound edges and all kinds of stuff like that. Okay, so link analysis, link discovery, network science is another amazing thing you can do with data without necessarily even knowing what the nodes and edges mean. It doesn't need edges to be labeled and nodes to be labeled in order to do interesting algorithmic work there. So given all these patterns and discuss that you're finding in your data, the real trick is, okay, which one of these patterns are actually useful and meaningful, or which ones are just a fishing expedition? Okay, you found an interesting thing. Okay, I like to tell people, for example, 6 Sigma. Anyone ever heard of 6 Sigma in quality management? Okay, I remember doing this at NASA. We had the 6 Sigma quality training as an astrophysicist working on astrophysics space missions. I didn't quite understand what they were talking about, okay, because 6 Sigma was born out of manufacturing. Basically, 6 Sigma means 1 in a million. Okay, so 1 in a million defects of an assembly line, of something manufactured on an assembly line, was a 6 Sigma process. If you only had 1 in a million of those. Okay, but it's really about quality assurance and quality management and risk analysis and so forth and so on. It's all, okay, but 6 Sigma, 1 in a million, is okay a rare thing when you have a million things. But if you have a trillion things, like we all have terabytes of data, we even have petabytes of data. So we all have trillions and even thousands of trillions of things. So if you have a trillion things, then something that occurs 1 in a million times will occur a million times. You will find the 1 in a million thing at random, and it doesn't mean anything because it's a random process. Well, assuming you have a random process, that's a whole nother story. But anyway, so something that's 1 in a million is not meaningful statistically if you have a trillion things. Or 1,000 trillion, now you're going to have a billion of them, okay? So the question is, how do you find the interesting things? How do you find the things that are most meaningful, the patterns from which you can start exploring and exploiting, and therefore extracting value? So I want to give an example of clustering analysis. So clustering analysis we're all very familiar with. Okay, so clustering analysis, basically we just take some data and we separate it into sort of natural, sort of logical segments. Okay, where the things within the groups, within the clusters, within error measurement of those things is small compared to the separation. Okay, and so things are most similar are together, and they're separated from the things that they're not similar to. That's all clustering is, okay? But as shown in the little cartoon here, you can take the exact same input data set and come up with different clusters. All right, so you can sort by color, sort by shape, you come up with completely different clusters here. Now in this case, it just turns out that there's 3 clusters in both of these examples, but it didn't have to be 3. We could have had 10 colors. So if I sorted by color, there would have been 10 clusters. If I sorted by shape, there would be 3 clusters. All right. Or you could sort things by the number of sides something has, okay? So triangles have 3 sides, squares have 4 sides, circles have 2 sides, the inside and the outside. Anyway, so in clustering, we have no idea what the right answer is. So this is the cold start problem. We can do clustering, but we don't know which of these is actually the meaningful one, which is the one that has some kind of optimal specification of our data, or optimal description of the data. All right, so we don't know what is the right number of clusters. Like I said, if we had 10 colors, we'd have 10 clusters in one case, 3 in the other. Which is right? I don't know. We don't know the semantic meaning of the cluster, so you apply this algorithm that separates things by features. You don't necessarily know what they actually mean. Okay, so you don't have the semantic meaning. Okay, so you don't know the number. If you choose different features, as we just showed here, you get different clusters. But even worse yet, if you change the similarity metric of what you define as similar or different, that changes the game as well. Okay, so all these things make your life a little complicated. So one way you can fix this problem, this is our first solution to a cold start problem. Again, you don't know how to get started with clustering if you're clustering customer data or health data or machine data or whatever data you're working with, banking customer data, things like this, whatever it happens to be. What do those segments mean? Which ones are optimal? Which ones are the real personas? I mean, so in marketing, we call these personas. Which ones are the real personas that we're going to market to? Or we all talk about personalization in marketing in seg one, segment of one. But the reality is it's really a limited number of marketing campaigns that the marketer has in their toolbox. And the individual will move from persona to persona. So if you're at work, you have one persona of things you might want to buy online. When you're home, there's another set of things you might want to buy online. When you're on vacation, there might be another set of things you buy online, et cetera. So your persona will move around. So that's personalization. You're not fixed in a box because you happen to be a white male over the age of 50 who live in a certain zip code. All right? I know that doesn't work because there's another white male over the age of 50 in my neighborhood who likes the Pittsburgh Steelers because he has a banner hanging out in front of his house. And I'm a Baltimore Ravens fan and hate the Pittsburgh Steelers, so clearly we do not have the same likes and dislikes. Okay, so every day I'm reminded that normal demographics do not apply in the big data world. Okay, so how do you know? So one way you know is you can apply a metric, and there's different names for these metrics, and they have different sort of mathematical finesse in them in different ways. But basically what you're measuring is how I want the most compact clusters you can give me, most compact relative to their separation. So when you find the most compact ones relative to separation, that will be my optimal set of clusters. I may not yet then still not know what they mean, but at least I can point to someone and say, when they say, well, gee, you separated by color, you got 10, you separated by shape, you got 3, what's right? I can tell you which one was the most optimal set of clustering. All right, so you can use this technique to measure, and there's different ways of measuring. In the equation, there's an example of the Davies-Boolean index, where you're basically measuring the intra-separation of data points inside a cluster versus the inter-separation of data points across clusters. That's all, just a ratio. That's really all it is, okay? And so given that, you can measure this thing, and what you want to try to do is minimize that. And you minimize that over a meta-learning process. A meta-learning process is hyperparameter optimization. Okay, what are our hyperparameters? It's the number of clusters, it's the distance metric you're using, okay, it's the choice of algorithm you have, it's the features you're choosing to cluster on, and so forth and so on. Okay, so you can iterate on this, measure this DBI, try again. It's getting better, getting worse, okay? If it's getting better, you keep moving in that same direction. If it's worse, you reverse track and maybe change it in another direction. So you keep doing this until you find some minimum in this function. So I gave a lecture on this to a bunch of summer interns at NASA about 12, 13 years ago. They asked me to give a talk on data mining, and I didn't know quite what to do because there was a wide variety of skill sets among these summer interns. I mean, some were doing hard engineering, some hard science, some data analysis, but some were just doing web development or clerical work or soldering boards for a satellite. Okay, so they had very different levels of mathematical understanding in the room, so I didn't know what to do. So I said, well, we all understand clustering because we separate our toys by color and shape and all kinds of things. So I thought this would work well. It's a natural human thing. So I showed that equation. I didn't explain it, and I walked away thinking that that was a useful exercise. But it was far more useful than I thought, because one of the interns in this audience was very different from all the other interns. I didn't know that at the time, but I found out very soon thereafter. So most of those summer interns were sort of the typical summer intern. They were what they call rising seniors. Okay, they say college. They're between their college junior year and college senior year. Okay, so they just finished their college junior year, most of them. This one particular guy was a rising senior, but in high school. He was a high school junior, youngest guy ever to go through that program as far as I know. He took this technique of DBI, finding the minimum compact clusters, smallest clusters relative to separation, most compact clusters, applied it to the problem he was working with his mentor that summer, who was a NASA senior scientist who spent 25 years trying to build predictive models of when you see events on the sun, they lead to activity on Earth, ionospheric disturbances, northern lights, southern lights, aurora borealis. These are examples, but also power outages, destroying communication satellites and causing cancer in airline crews who fly over the poles. Okay, so there's a lot of negative effects of these things. So you want to build a predictive model. This scientist had spent 25 years trying to solve this problem. How do you predict this? This high school junior solved the problem with the clustering technique I taught him. You might say it was disruptive. That NASA chief scientist called me in the office pretending to be angry. He said, "What the hell did you tell this student? He just solved the problem I spent 25 years trying to solve." And then he smiled. Because what the student did was not only did he do this compactness of solar parameters, Earth parameters, there's a strong correlation between what happens on the sun and what happens on the Earth, but he did something very, very smart. All right, and this is where you can start doing some really smart stuff with your cold start analysis. Maybe the tightest clustering doesn't happen at the same time, it happens with a time shift. So he time shifted the data, 0, 1, up to 12 hours. Okay, he did these time shifts and found that the tightest correlation between certain physical things we see on the surface of the sun correspond to events in the Earth's ionosphere 2 to 4 hours later. And these are the things you see, and here's the time window when it happens. There's that minimum. Now, it's not a sharp minimum, but it's a minimum. All right, so the scientists knew that this existed, but they never knew quite what were the predictive variables, and this young man discovered them through this analysis. Okay, so here's a guy, junior in high school, probably never had a 3D magnetohydrodynamics course before in his life. He probably didn't even know what that was. Okay, probably had a physics course, but maybe not. He basically, that's about as cold start as you can get, and he solved a problem that a NASA senior scientist has spent a quarter century trying to solve. All right, so to me, that's like the best poster child story of this problem, is taking someone who really has no clue of the domain and yet can apply this technique to finding a really interesting pattern that can now explain the things that the scientists have seen, but they never could figure out what were the parameters that were most informative and explanatory for what we're seeing, and this person found it. All right, so there's a lot more examples here. I know my time's going to run out. I'm not going to go through all these examples. I'm going to go through a couple of them. So at the very last slide, there's a link on the last slide, so get ready for that. There's a link on the very last slide, which is not here yet, but it will get here in a little while, to these slides. And so you can get download the slides, you can read through the examples that I'm not going to spend much time on. But there's all kinds of examples here, and I would love to just walk you through all of these. And I actually did a workshop at a conference on all of these, and so it really took 4 hours, not 40 minutes. And I guess you're not going to give me 4 hours, right? Sorry. No, I guess not. Okay. So I would always tell people that what the key point in this is, especially in unsupervised learning in general, is let your data be your model. Let the data tell you about itself. Okay? That's why data profiling is such an important thing. Understanding your data, getting up close and personal with your data. Finding what its mins and maxes are, what its segments are, its trends, its correlations, its outliers, its anomalies. Finding all the interesting things in your data, that data profiling step. I like to call it having a first date with your data. So have that first date with your data, find out these things, let the data talk to you, let it explain things to you. All right? So k-nearest neighbors is an example of where the data actually literally becomes the model. Familiar with k-nearest neighbors classification? Okay, so basically you have a new data point and you measure its distance to k or some number, so k just represents a number, let's say 100 or 1,000 or some number, and you look at those nearest neighbors and you see what the classifications are of those nearest neighbors, and whatever the majority class is among the nearest neighbors, that's the class label you assign to the new data point. That's all it is. All right, so it's supervised learning, because all these things are labeled, the new thing is unlabeled, and you put it in that space, measure the k nearest neighbors classifications, take the majority, you're done. You've classified this new data point. So why is this in this particular slide deck? This is a supervised learning algorithm. The reason it's here is because, as I learned, after the first, back up a second, I taught a data mining course at the University of Maryland starting about 17 years ago. And I taught a lot of these algorithms in front of the class that I had been reading about for 3 years. And I thought I understood it, but I did not understand it until I stood up in front of someone and tried to teach it to them. So that's my lesson. The best way to ever learn anything is to teach it to someone. So if you've ever had a chance to do a workshop at a conference to teach about what you're doing, go do that, please, because that's the best. I mean, I was giving lectures on neural networks, and it was like the third semester into this course, believe it or not, before I had the aha moment that I said, "Oh, that's what backpropagation means." And so I had one of those moments with this. I said, "Yeah, okay, nearest neighbors, supervised learning." It was in the supervised learning part of my course lectures. And it occurred to me as I was talking, I said, because I had spent the earlier part of the semester doing unsupervised learning, and part of that set of lectures, I gave a whole lecture on distance metrics, similarity metrics. So you may be familiar with some distance metrics, cosine similarity, Jacquard similarity, Euclidean distance, Manhattan distance, p-norms. Some of these things sound familiar, hopefully. Okay, so I had given whole lectures on these distance and similarity metrics. And as I'm talking about this, I realized the answer to this problem, that is the class you assign to that unknown point, depends upon the nearest neighbors whose that list itself is determined by a distance or similarity metric, which is not given to you. Nature didn't walk down and said, "Hey, I want you to use Euclidean distance on this one, but I want you to use Jacquard similarity on that one, and I want you to use cosine similarity on this one." There is no word from on high that says, here's the distance metric you use in this case when you're using k and n, and this other case when you're using k and n. So now that becomes a cold start problem because I don't know which one to use. But how do you know? It's actually quite simple. You try different ones, just like the meta learning thing we did with the clustering. You try different ones. You measure the accuracy because you have training data. Remember, supervised learning, you have training data. You measure the accuracy. You measure precision and recall. Did I get how many false positives, false negatives that I get? So you measure those things. You measure F1 score. Some way you're measuring your performance, and you find the distance metric that performs the best. That gives you the highest precision, highest recall, lowest false negatives, lowest false positives within your cost model, because sometimes a false negative is far more expensive than a false positive, for example. But within your cost model, within that data set, you find the optimal solution by trying different distance metrics. So what's interesting about that is I started to think that after a while, almost everything that I was doing that I was calling supervised learning had a step in there where I was sort of making an assumption about what I was doing, and that assumption in itself is an unsupervised thing. Right? And so there's sort of this yin and yang, there's sort of two faces of machine learning, which we call supervised learning and and unsupervised, that are actually sort of two faces of the same coin. And someone actually wrote an article about this, so there's a link here. When you see links like this, again, when you download the slides, you'll be able to click on those things, so don't try to capture all this right now. If you want to take a picture of anything, make sure you get a picture of the last slide, which is where I have the link to the slide deck. But anyway, so they're really pretty much the same thing. So when these data are coming streaming down, all right, and you have data streaming in, and you're starting to do something with it, like this poor fellow, he doesn't quite know what to do. Do I sort it by shape, by color? Okay, so I love this because this works really well in kindergarten classrooms. Okay, so I've had some experience talking to young kids about data science, and again, not at an algorithmic level, but as an experiential level. Okay, so they know they can build castles with blocks. They can play soccer with balls. Okay, so they're already doing not only sorting categorization by shape and color, but also by functionality. Highly intelligent little people their clustering metrics or features are a little bit more sophisticated than we give them credit for. We think color and shape, that's all they can master. Well, no, they already know the functionality of blocks and balls, right? So they can cluster that. Okay, so now you got these other things in there. What are those? Okay, so you're going to classify these things eventually. Okay, so you've discovered these patterns. These patterns hopefully have meaning. When you discover they have meaning, then you put a class label on it, and now it becomes supervised learning. So the next time you see a ball, you know it has these capabilities. You see a block, it has these capabilities. You see these sort of orangey, goldy, whatever color that is, things that has some other capability. Okay, so now you've gone through this process of doing the optimal pattern discovery through unsupervised learning through domain expert talks, what these things mean, so that you can now put a class label on it, and then pattern recognition kicks in. The next time you see this, you know where to go with it. Okay, so I have a few sample walkthroughs. How close are we? 10 minutes? Oh, there you go. I should have said 20 or something. Be careful what you tell people; they'll believe you. 20 minutes to go, right? So some examples here. I want to talk about, like I said, some of these a little more detail than others. The one I'm going to spend less time on, which has the most slides, is the middle one there, called the ways of Bayes. It's about Bayes classification, and part of the reason that I won't be giving you detail is the very reason I just said. Most of the slides are on that one, so you can walk through on your own on that one, because all the details are there. So regression is an example, a really great example of a problem that is, in a sense, it's unsupervised, because you're not saying what this trend means, but you're fitting a curve through it. Okay, so you have some data there. And you can do a 2-parameter model, which is basically a line, a slope, and an intercept. Or you can do a 3-parameter model, which is a parabola. Okay? Or you can do a multi-parameter fit, which is a higher order polynomial. All these polynomial solutions to regression actually have closed form solutions. You actually can write it down. Okay? So if you ever learned about determinants, remember those things in high school math? You could actually solve for these parameters, these fits, okay? Linear, polynomial, quadratic fit, cubic, whatever. You can find those parameters. And what you want to do is try to get a model that is generalizable to the data, all right? You don't want to underfit, that is, there's more structure in the data than you put into your model. For example, that line up there in the first panel, that's underfit. We call that bias in statistics. There's more structure in the data than your model takes into account. There's more structure than a 2-parameter model. So when you don't take all the features into account in statistics, we call it bias. In human life, we call it bias. Okay, when you don't look at the full feature of something and you make a decision without knowing the full story, that's bias. Okay, but in statistics, it's a statistical technical term. Okay, we don't want to underfit, but also we don't want to overfit, where we now are modeling all the bumps and wiggles and variance in the data. Okay, so it doesn't generalize to the data. Whereas the middle panel probably does generalize well. So if there's some future data point, we'll have a pretty good general idea what it will be based upon that model. So one thing we know about these higher order polynomials is what happens to the polynomials beyond the 2 endpoints. They take off, because there's nothing to constrain them in your data. All right, so that is a really horrible fit. But okay, so we have closed form solutions. So where's the cold start here? The cold start is we don't know which of those we should choose if it's in higher dimensions. Okay, we can look at this one, and yeah, I can do that. So what we do is we set aside a validation set. Okay, so we fit a curve through the data, and we see what sort of the mean square error is for the data points. We're minimizing that. Again, we have a closed form solution from math for the solution with the training data. Then we look at the validation set, the holdout set, and say, what's the mean square error of those points relative to that curve we just put through our data? And okay, it can start getting better and better and better as you find different parameterizations. For example, a line, a parabola, a cubic, a quad, a higher order polynomial, whatever. And after a while, we can just keep getting better and better and better. So what we're doing, if we just only look at the training data, we're overfitting. Eventually, you can get a higher order polynomial that goes through every single point in your data, which means nothing. But you got 0 mean squared error in your training model. Worthless. Okay, how's it doing against the unseen data, the holdout set? Well, initially you're improving, hopefully. Hopefully you're going in the right direction. You're improving, so the yellow curve there. But after a while, it starts getting worse. Okay, or it stops improving basically, because now your model in that sort of pink curve is overfitting, but it's not helping with the real data, which has natural variance. Okay, you don't want to fit the natural variance in the data. It's called natural variance for a reason. It's the natural variation in your data. You shouldn't try to fit it. Okay, so there's an optimal place to stop. Okay, so this is where the cold start comes in. You can try different regression models. And they don't have to be even polynomials, okay? They can be other complex functions. Okay, so you can do function discovery, which is another cold start problem. Okay, and you stop when you start seeing a change in the behavior of your holdout set, your validation set error. Now, normally it doesn't look like that beautiful thing I just showed. Normally it looks like something like this. So this is a real world. This is a real case. The other thing was schematic. Okay, you keep improving, and then it just sort of like levels off. Okay, so where that elbow is, the point that I'm pointing out here, that's sort of where now it's just sort of like you're not really fitting anything else. There's sort of natural variance. You're never going to get any better at fitting that, no matter what you do. Okay, so you want to back up to that point where that transition occurs, and that's your optimal model. So now you can not only just do a regression, but you can say this is the optimum regression for this data set. Okay, so that's our cold start. We can do it, all right, but we don't know which one's best, but through this technique we can do that. So k-means clustering is another example for another reason. We already talked about clustering a little bit earlier today, about that compactness of clusters relative to separation. All right. K-means clustering is a technique. Familiar with it, people? Okay, so there's lots of Ks in data mining. If you're familiar with K nearest neighbors, K-means clustering, KD trees, K item sets. If you're familiar with market basket analysis, Ks are everywhere, which I love it because I have 2 Ks in my first name, so that's kind of cool. Okay. So K-means clustering always bothered me that you have to assume in advance the value for K, which is the number of clusters. You're making an assumption. Remember I said earlier, if you start making an assumption, something that's not handed down to you from on high, you're really in that cold start place. Because how do you know your assumption is right? How do you know? Okay, so K-means clustering says, well, we can start varying that K, just like the example I showed with that high school student did. You can start meta learning, changing the value of K, changing the distance metric, change the features you use. Okay, but here's a very simple case where we're going to do that. We know that there's 2 clusters here, and I like to give this data a story. It's a made-up story, but data storytelling is my number one most important thing I tell data science. You got to tell a story with your data. Okay, so it's a made-up story, but it helps understand this case. All right, I have some data up top. Okay, given the data, that's the top row there. And I'm going to assume 2 clusters. Why 2 clusters? Because these data, this is phony story, but here's the story. 2 families merge, okay? A divorced wife, divorced husband, they now marry a new family, okay? So now you have a bunch of kids and 2 parents, okay? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. We have 9 kids, all right? Now maybe you don't know which family those kids come from. The mother's side, the father's side. Family merged, we have 9 kids. All right, again, made up story. This isn't a true story. Okay, so you take these data and you try to figure that out. Okay, so I did a real clever thing. I sorted them in an ASCII way. Okay, first 1, then 1, 0, then 1, 1, then 1, 2, then 2, then 2, 0, then 3, then 3, 0. Okay, that's a pretty useless thing to do. Okay, and so I'm just going to make an assumption that there's 2 clusters here because there were 2 families. So there must be 2 groups. Okay, that's a reasonable assumption. So maybe that assumption from on high works in this case. But I have no idea how to sort these out into which family they came from. And maybe my model is wrong at the end because all models are wrong, but some are useful. So this is another case where this model might be wrong at the end, but it's going to be useful. So the way K-means clustering works is you make another set of assumptions. You assume the value for K, which we just said is 2. The other thing you assume is you assume the mean value for your 2 clusters. So the mean value for the clusters, the mean of its members, is the label for that cluster, by the way. The label for that cluster is its mean value, all right? Just think about it as age demographics, under 21, 21 to 30, 30 to 45. Okay, it's a mean value, i.e. a range, that's the label. But we have no idea what that is. So what you do is you just make a totally random guess. Cold start. So I said, okay, let's assume the mean ages, because I know there's some youngsters in this family. There's a 3-year-old and a 4-year-old, okay? They seem kind of close together in age, so maybe they didn't come from the same family, okay? Poor woman to have 2 children back to back like that. Okay, so I'm going to assume that the mean ages of a 2 clusters, 2 families, is 3-year-old, 4-year-old. Pretty stupid assumption. But amazingly, k-means clustering fixes my stupid assumption. Wonderful. It knows how to fix my stupid assumption. So if you walk through this process where k-means clustering, you say, go through all the data row, all the points in the data, go through that whole row of data, and assign each member of that data set to the cluster that is closest to the mean. Then you have a new set of clusters. Then you recalculate the mean, do it again, recalculate the mean, do it again, and finally, it stabilizes, it doesn't change anymore. So you can walk through this, it's all there, it's all there. You can walk through this, and you end up with something that doesn't look anything like 3 and 4, but the mean ages of the 2 clusters at the end are 7 and 25. So I started with a really ridiculous assumption and ended up with something that actually makes sense. There's a set of children who are in the low end range and a set of children in their 20s and 30s. That makes a lot more sense as the 2 group of the family. So starting with 0 knowledge from the set of data points, I actually found 2 meaningful clusters and maybe actually a solution. Okay, so that's I need to wrap up. Like I said, there's a lot more on the slides here. I'm going to step through them, but you have at your leisure a chance to read through them all. All right, so backpropagation and neural networks. I'll just throw this out here because I'm sure you're going to hear about TensorFlow a lot today and neural nets today. So that we typically think of neural networks as a supervised learning thing, but what is the cold start? We have no idea what those weights are in those edges. So normally you assign an arbitrary value. You assume that the weight equals 1 between all the nodes and all the edges and all the layers. Pretty stupid, right? Well, just think what we just did. We did something pretty stupid, and it actually converged. So what backpropagation does is it figures out how your accuracy improves as you adjust those weights in different directions. So you're basically doing a gradient descent, trying to find that sweet spot in a very complex space of where you minimize the error of the outcome by applying the error correction from backpropagation. So you start with a cold start, assuming all the weights are equal to 1, and you actually end up with something that actually is useful and works. So we're working in very complex spaces, and I will stop in a second here. So I love telling the story of another way to do this is apply genetic algorithms. So anyone ever used genetic algorithms? It's a wonderful technique to explore very complex spaces because oftentimes we're trapped in a local minimum or a local maximum. Okay, so if you're applying gradient descent, you can just end up at a local minimum, local maximum, but there is a best solution out there. So genetic algorithms helps us to find that. And the classic example of this is someone tried to design an antenna using an objective function, which is beam efficiency, isotropy of the radiation field, all kinds of objective measures of a good antenna. And they discovered that the classic antenna was not the best antenna. This was the best antenna. All right, so there's a lot more on these slide decks, and they're throwing me off the stage, so I will jump right to the end slide, and there's a lot more that was there. So go to kirkborne.net, DevFestDC 2019. You'll find all the slides, emails there if you have any questions, so thank you very much.